This is a joint work with Dani Gamerman and Marina Pais. So, first of all, I'm going to give you an introduction about the problem. Then I'm going to talk about modeling point patterns. Next, I'm going to show you a model with regression coefficients varying over space and time. Some results about an application will be presented, and some conclusions. Suppose we observe a particular event in an area of interest like that one. The event, which is usually unknown, in our case is known, but the locations of occurrences of the events are unknown. So, as example of events, we could cite infections of trees by a plague, deaths from stroke, or stealing cars. And the set of these locations is called a point pattern. A point pattern is usually the result of a dynamic process that occurs in space and in time. For example, if the event of interest is the infections of trees by a plague, this process evolves over time as new trees are born and older trees die. So, the spatial point pattern resulting from this process has a temporal dynamic. When you have that type of heterogeneity, requires flexible models to capture this spatial temporal variation. So if you have due reference data with the precise spatial location, we have to use a study of point patterns. And in this scenario, connections with explanatory variables arise naturally. For example, in the case of the trees, the infections of trees by a plague, the agronomist could be interested in if there are effects of spatial and unit-specific covariates in the pattern, and these effects change over time. With this information, we have to design a plan to intervene where and when the infections of trees is larger. So, the spatial temporal point process are the models for these types of data. The literature for analyzing data with spatial temporal heterogeneity is well developed. For example, Briggs and Deagle 2001 describe a flexible class of spatial temporal point process based on log-Gaussian Cox model. Deagle et al. 2005 describe a class of models similar to Briggs and Deagle 2001, but they included deterministic spatial, temporal, and spatial temporal components. Hayes et al. 2013 use not only deterministic components, but stochastical also components, and they included a dynamic structure in the temporal component. So these papers, they assumed the effects of the covariates when they are considered to be the same over the space. It could be appropriate in many practical situations, but it's not a realistic assumption when we have data set with a large spatial temporal heterogeneity in the effect of some explanatory covariates. So, we would like to consider here in this work spatial and unit-specific covariates. So, the purpose of this work is to propose a class of model that allows spatial temporal variation of the effects. To define a spatial point pattern X, we have to define its components. A spatial point pattern is a set of X indexed by S when these elements are equal to 1 if the event of interest occurred in S and 0 otherwise. And homogeneous and non-homogeneous Poisson process with intensity function denoted by capital lambda are the most common model for this spatial point pattern. Another useful class of models for a spatial point pattern is the log-Gaussian Cox process, where the intensity function is random and the log of intensity function is a Gaussian process. Here we have the definition of isotropic Gaussian process in expression 1, and here it's going to be denoted by the expression in 2. So far, we have talked about point pattern indexed by S, meaning space. Suppose now the point pattern is indexed by S and T, meaning space and time, with intensity function also indexed by S and T. This is a spatial-temporal point pattern, and it's the object of our study. Reminding you, in our context, we have spatial covariates and unit-specific covariates. So, to define the likelihood of our model, we have to consider collections of Poisson point patterns and intensity functions, indexed by V, where V is a configuration of covariates, unit-specific covariates. For example, if we have gender, male and female, and the marital status, marriage and non-marriage, the space with all configuration is going to be male marriage, female marriage, male non-marriage, and female non-marriage. And the likelihood in this scenario is given by the expression in 3. So, this is the model we are proposing. We have a collections of Poisson point pattern with intensity function capital lambda. The intensity function assumes a multiplicative decomposition with RSTV. It's a norm offset. The lambda, as we can see, is functions of spatial covariates, unit-specific covariates, and a random intercept. The model allows the effect of spatial covariates beta to vary over time, as expression given in 4, and the effect of unit-specific covariates is given by a sum of 2 components. One of these components, alpha star, it's allowed to vary over space and time according to the equation given 5, where eta is a temporal correlation parameter and eta depends on t and u. We have the same situation here for the random intercept. Here we just reparametrize the model, so now alpha is the effect of unit-specific covariates, and W is the random intercept. They are stationary and isotropic Gaussian process in space, and autoregressive and stationary in time. If you would like to consider a non-stationary model in time, we have to change the last 2 equations for equations similar as the expression in 7. Here we not included interaction between spatial covariates and unit-specific covariates, but they can be included easily. So, the likelihood function for the model depends on unaccountable functions, and this poses a difficult problem to handle. Exact solutions are only available in very limited cases, and even then, they depend on a number of issues. Some of issues are associated with dimensions of the number of occurrences, which is usually very large. So one reasonable option is considering a discretization of space and time. So here are we gonna follow Beans et al. 2002, and the space it's gonna be partitioned into subregions, and the time and into time interval equally spaced. With the discretization, we enforce homogeneity of the intensity, and the integral presenting the likelihood becomes the expression given, in 8. So, intensity discretization is found in many papers, like Miller et al. 1998 and Gammer 1992. Moreover, Van Gepeters in 2004 shows that the posterior distributions of the intensities converge to the posterior distribution of continuously varying intensity when the volumes of the subregions tend to 0. And if we use the discretization of the time and space, the likelihood is going to give him an expression in 9. So our object is going to make inference about the unit-specific covariates, the effects of unit-specific covariates, the effects of spatial covariates, the random intercept, and the random the hyperparameters. So we consider prior independence. So our prior distribution is given by the expression in 10. And now I'm going to talk about some details about the data we use in an application. So we have the zip codes where cars covered by insurance have been stolen in Rio de Janeiro. Almost 24,000 cars were stolen between 2009 and 2011. The time was discretized by semester, so we have only 6 periods of time. We have 2 unit-specific covariates available. Year of manufacture of car, it's a continuous variable, and car type, it's a categorical variable. Using these 2 unit-specific covariates, we have 22 different configurations. Well, the locations in Rio de Janeiro reflect different socioeconomic backgrounds. Great incentives to buy cars were experienced by the population in the recent years. So the theft pattern may be affected by this variation, and effects should be as flexible as possible. For example, is passenger car theft decreasing in some areas of Rio de Janeiro over the last years? These questions can only be answered by allowing interaction among effects of covariates, space, and time. We use a model stationary and isotropic in space, and autoregressive and non-stationary in time. So we use vague priori to mean and precision of the Gaussian process. We use the exponential correlation function. The prior of the range parameters was used as suggested by Fonseca and Steele 2011. And wiki identification of the range parameters were experienced. This is a well-known difficulty of spatial models, more pronounced here, because we have more than one range parameter to estimate. Following Liang et al. 2009, we fixed the ranges at the median of the observed distance, and no significant changes for the likelihood parameters were observed, but stabilized results for the hyperparameters were obtained. The offset were taken as populational size, so we have to know the number of the days covered by insurers of all cars with configuration V in the region K in the period of time T. And to obtain this information, it's not an easy task. So the result I'm going to present is based on the 21 regions partitions. We use the first 3 digits of the zip codes to obtain this partition. The results were obtained via MCMC methods using the ring bugs. We took care of convergence and correlations, and the resulting sample considered of 2,000 draws. So here we have some results about the first unit-specific covariates, the year of manufacture effect. We have the posterior median and the credibility interval of 1 period of time. So as we can see, we have a spatial variation here, and the same was observed for the other periods of times. Positive coefficients indicate a greater intensity of thefts of new cars. Negative coefficients are associated with western regions of Rio de Janeiro. The largest range of the credibility interval is observed at the region 3. It's because we have a scarcity of information here. It's just a small island in Rio de Janeiro. So here we have the year of manufacture effect over time for some regions. So as we can see, we have a temporal variation here, and looking for the spatial variation and the temporal variation, we can say of the effect of year of manufacture vary over space and time. We have some results for the type car effect. Again, in one period of time, we have this spatial variation. Positive coefficients indicate a great intensity of test of passenger car because the reference is non-passenger car. The largest coefficients observed was downtown. And here we have the temporal variation of the type of car theft. And again, even considering 6 periods of time, we have a temporal variation for the effects of this covariate. Here we have results about the random intercept, W. The random intercept is responsible for capturing the main spatial temporal variation not captured by the covariates. So it has to compete with covariate for spatial and time variation in the model. As we can see, we have still spatial variation and temporal variation for the random intercept. Well, here we have the posterior histogram for the Gaussian process. It's not precision because we have the mean in the top and in the bottom we have the precision. So as we can see, we have concentrated posterior for the hyperparameters, considering vague priorities. Some conclusions about the work. We have a hierarchical formulation to handle point patterns subject to effects of covariates with large spatial temporal heterogeneity. And the results show the model can capture the spatial and the time trend of effects, even considering a few periods of time. Well, that's it. Thank you.